All right, good afternoon. I am going to try to do this presentation a little differently than I have in the past. I'm hoping that it will work. This is kind of a harder lesson to teach um, over the computer. So I do have my periodic table with me. If you have one, I would highly suggest you getting one right now because we're going to go through this in this particular portion of the lesson. So, of the three subatomic particles, protons, neutrons, and electrons, only electrons are directly involved in chemical activity. So, we're going to be looking at the electrons here. Now, electrons occur in energy levels called electron shells. So, when we talk about this, we're going to be talking about how we organize the periodic table with this information. Atoms may have one, two, or three electron shells surrounding the nucleus. The number of electrons in the outermost shell determines the chemical properties of an atom. We call these valence electrons, and I'll get a little bit more into those. The valence electrons are electrons in that outermost orbital. Those are the ones that are involved in bonding. Those are the shells that are not full. All right, so they want to fill those shells in order to be stable. The atoms that have full outer shells are referred to as the noble gases, and they do not react. Well, again, we'll kind of get into all that. So atoms with incomplete outer shells tend to react so that both atoms end up with a completed shell. So that is their goal, to get a completed outer shell in order to be stable. They can do so in a couple of ways. They can either share those electrons in their outermost shell, or they can give off electrons, or they can receive electrons. Either way, whether they're sharing or giving and taking, those are referred to as chemical bonds. We're going to talk about Lewis dot structures. Now, due to, like I said, the lack of space, because we have our protons, remember, in the middle that have their buffer, their neutrons, but we also have the electrons on the outside. And so the electrons are trying to get organized so they can maximize the distance between them because they repel each other, but minimize the distance between them and their protons that they're attracted to. And because the first energy level is so small, it's so close to the nucleus, there's not a lot of space. So that first energy level, which can also be called a period, can only hold two electrons. So if I look at my periodic table, I look at hydrogen. So if I get my pen to work, I look at hydrogen. Okay. Hydrogen, if we do our protons, if you look it up on your chart, hydrogen is number one. Atomic number is one, so it has one electron. If it's got one proton. If it has one proton, it has one electron because we want to stay neutral. Now, if you look at the mass is, again, I'm looking at my periodic table, the mass is 1.0078. So if we round, the mass is 1, which means we do not have any neutrons. So there's what I refer to as my pen: protons, electrons, neutrons. Now, what we're going to do is we're going to pretend that there is a box around our element. Now, we're not going to really draw this box, but we're going to pretend, because other than that first period, all the other periods or shells have four. So let's not do that. Let's do 1, 2, 3, 4 orbitals. Each orbital can hold 2 electrons. But like I said, that first shell, that first energy level is too small. So it will only hold 1 orbital. So we only have 1 face on our box. Oh, now I'm going to have some help here. So right now with Lewis dot structures, we're only concerned with electrons. Those are the ones involved in bonding. And so when I draw my hydrogen, I want my hydrogen here. You put your symbol for your element, and then the dot will represent that 1 electron that hydrogen has. If we go all the way across the other side, and there's a reason why it's organized this way. If we get to helium, I'm going to stay with red. If we get to helium, helium has an atomic number 2. So it has 2 electrons. And if I look up the mass, I think it's 4 something. Yep. So I have 2 neutrons. All right, so when I draw helium again, since it's in that first energy level, I only have one face of my block. And so I'm going to put my 2 electrons. And now that energy level is full. So because it is full, it is called a noble gas. It is unreactive. This is why hydrogen is flammable and helium is not. So we say that this one has 1 valence electron. Right? Valence electrons are the number of electrons in the outermost energy level, and then this one would have 2 valence electrons. Now, bonding has to do with how many unpaired electrons I have. Well, this little guy right here is unpaired, so I can form 1 bond. Now, I don't have any unpaired electrons with helium, right? We got a pair right here. So 0 bonds. Again, that's what makes it inert or a noble gas. Okay, so that's my first energy level. If you look at your periodic table, right, that is the first, we call them periods that go across. Right. So I've drawn this out on my board at school. And so you can see I have that here. You can see my PEN for both of them, and then my Lewis dot structures. So again, period 1, 1 orbital, 1 face on our square. Now let's go to different color. Let's go to period number 2. So that's the next row underneath. We're going to start with lithium. Now lithium, if we look at our PEN, right, our PEN, it has, it's 3 protons, 3 electrons, and it has a mass of 6.9, so I'm going to round, so that'd be 4. Now again, if you guys did these maybe in your earlier history of science, maybe you know, like you have the nucleus here, and so you're going to have your 3 protons. I'm not going to bother with the neutrons. That'd just be messing there. But then maybe you did your first energy level, and then it has 2 electrons. It's full, and now our second energy level has 1. So again, we're not concerned with this energy level because it's full. It can't form bonds. But this one right here has 1. So I'm going to put my 1 dot here. Notice it looks a lot like hydrogen because when we look at our columns are up and down, those are called families, and they're called families because they resemble one another. Right, so then if I go to the next one, that would be beryllium. So again, beryllium, my PEN, my PEN. So I have 4, 4, and 5, because my mass is 9. So again, my protons and neutrons equals my mass number. So that's 9. So again, if I do my beryllium, if I have my beryllium in there with the protons and the neutrons in there, I would have my first 2, which I should do this. Because my first energy level, remember I did it red. So that would be my first 2 electrons. And then my next energy level, that's why we're in the second period, we're in our second shell here, would have 2 again. So we have, here's my 4, right? Now, I am not going to pair electrons because, again, they're trying to maximize their distance. So I'm going to put them on separate sides. Now, it doesn't matter if I did it this way or if I did it this way, or in my class, I don't care if you put them together, but generally, again, we want them to space out as far as possible. Now, if I was to continue this trend across, this is what I'd end up getting. So there's my lithium, my beryllium with the 2. Next would be boron 3, carbon 4, nitrogen 5, 6, 7, 8. Notice when I get to 8, I am full. And again, this is a noble gas. I always want to write Nobel, like a noble gas, like Nobel Prize, noble gas, or inert. Okay. It doesn't have any unpaired electrons, so it can't form any bonds. Lithium can form 1 bond, beryllium can form 2 bonds. Notice my 3, 4. Now nitrogen only has, notice here, here, and here. Those are the unpaired, so it can only form 3, 2. This one is wrong. This should have 7. So that would be 1 bond. Okay. All right, and then we have this shell is full, and now I got to move to the next energy level. Okay, so if I move to the next energy level, let me use purple. So I start with sodium. Okay, and again, sodium. Now, if you're starting to get this trend, you should see that hydrogen had 1. Lithium has 1. How many do you think sodium has? 1. And that's because, again, it's in that first family here. It's in the first column. The second column is going to have 2. We're going to skip this D block in the middle. I know it's hard to see when I have my share screen. We're going to skip the D block and go all the way over here. And then we are going to have 3, 4, 5. So we're going to follow the same trend, right? Because, and let me explain why. The sodium has 11 electrons, right? 11 electrons. So remember, 2 went into the first period. 8 went into the second period. So I'm up to 10. So I'm going to have 1 in the third period. Okay, or again, you can follow the trend. Column 1, 1 electron. Column 2, 2. Jump over to 13, 3. And you're going to skip those 10 in the middle. And you're going to keep going. So we can see here is our third period. So notice how this is a family. This is a family here. We call these a family. My pen just decided not to work. All right, so this is a family here. Notice they all have 1 valence electron. They behave very similarly. Same here, right? 2, 3, 4. These are families. So all of them underneath are going to have the same valence number of electrons. So again, 1 bond, 2 bond, 3 bond, 4, 5, 6, 7, 8. Boom, noble gas. Got to go to the next period. Okay, so I hope you understand how to do Lewis dot structures and number of valence electrons. So again, if I go back here, yes, sodium had 11 electrons, but it does not have 11 valence electrons. Valence electrons are the number in the outermost energy level. So sodium only has 1 valence electron. Magnesium only has 2. Aluminum has 3, right? Silicon has 4. And so that's the number of valence electrons in the outermost energy level. All right, so hopefully this makes sense. So I can go all the way down to cesium. Cesium is atomic number 55. So it's 55 protons, 55 electrons. I'm not going to count all that. I just know that cesium is in underneath lithium, sodium, potassium, rubidium. That whole family has 1 valence electron. All right. So you should be able to determine that by looking at the periodic table and figuring out how many valence electrons. Other than the D block, that D block is in the middle there. It usually says D orbitals. And so those are what we call transitional metals, and they don't behave like they are supposed to. So we will not talk about that in this class. So the strongest kind of chemical bond is a covalent bond, and that's where 2 atoms share 1 or more outer electrons. 2 or more atoms held together in a covalent bond form a molecule. So here is where we have our hydrogen, right? So we have our hydrogen with our 1 valence electron. If it looks like this, right, they share two, it resembles helium. And that's a noble gas. That is stable. So what's going to happen is two hydrogen atoms are going to hook up. And that's why we always write hydrogen as H2, because it's rare to have just one, especially since it's a gas, to have just one atom of hydrogen. So they're going to find another atom and they're going to hook up and be stable and very happy in this configuration. They're going to share. That's what that bond, that little bar here, maybe you've seen this before. What that means, that line is representing a pair of shared electrons. There are so many different ways that we can show this. So again, we have the orbital diagram, we have a space filling model, or we just have our structural formula. Now, sometimes we can share two pairs of electrons, and that's called a double bond, or three pairs called a triple bond. So atoms in a covalently bonded molecule continually compete for shared electrons. The attraction of pole that an electron has is called its electronegativity. The more electronegativity an atom has, the harder it's going to pull. So when we look at electronegativity, again, this is how badly does it want an electron? All right. So I'm going to go back. Okay. So for instance, fluorine. Remember, fluorine has 1, 2, 3, 4, 5, 6, 7. Fluorine just needs to get one electron. If it does, it's full. It's met octet. Octet is the term we use when we have met all 8. We got 8 around that outer orbital. Of course, not with period 1. Remember, period 1, we can only max at 2. But all the other periods, we max at 8. It's met octet. That means it's stable. So fluorine is very electronegative. It wants electrons. It will take electrons from other atoms. It's a little, anybody in that fluorine family, fluorine, chlorine, bromine, they're very greedy. They're very electronegative. On the other hand, we have lithium. And remember, lithium only has 1. If it can get rid of that electron, remember the inner energy level is full, has met octet, and then it will be stable. So this has a low electronegativity. So it's low. Does not want electrons. It'd have to get 7 more electrons to meet octet, where this one has a high because it just needs 1 and it's met octet. So again, electronegativity is how badly does an atom want electrons. So in molecules of only one element, the pull towards each atom is equal. So if you're doing hydrogen versus hydrogen or oxygen versus oxygen, it's like a tug of war where they're at a stalemate. They're going to share evenly because they're evenly pulling on those electrons. These are referred to as non-polar covalent bonds. So we're going to describe 2 types of covalent bonds. They're sharing, but in one case they share evenly, in another case they share but not evenly. So when they share evenly, they're non-polar. Water is a molecule that has 2 different elements, right? It has oxygen, H2O, oxygen and hydrogen. They have different electronegativities. We look at oxygen. Oxygen, in fact, has this Lewis dot configuration, right? I can look at that, count over 1, 2, 3, 4, 5, 6. So 6 valence electrons. So it just needs 2 more. 2 more and it's met octet. Hydrogen, poor hydrogen right here. Hydrogen is, how do I put this? Hydrogen, like, it only needs 1 more to look like helium, but it also can lose that electron and then have no electrons, right? So hydrogen is kind of this anomaly. It's kind of weird, which is there's some other properties that are weird about it, but I'm not going to get into that. I'll let your chemistry teacher get into that. So what happens is we just know that oxygen is more electronegative, and because it is, when we have our oxygen, we're going to put our 2, we call these lone pairs up here. I'm not going to get into bond angles. Chemistry will. We're going to put our little single ones here. Okay, I've kind of spaced them out. So hydrogen will be here. And here's my other hydrogen. Now notice I've got 8 around oxygen, it's met octet. I have 2 around hydrogen, it looks like helium. We are going to share. These are covalent bonds. But what we're going to say is oxygen is going to say, yeah, no, I'm going to pull these electrons closer to me. I'm a big bully. I'm a little selfish. I'm going to pull it closer. Because it pulls it closer, this part of the molecule gains what we call a delta. Delta means change. This is a lowercase delta. It means partial. So this part of the molecule has a partial negative. This part of the molecule will have a partial positive because that proton's positive charge is not completely being negated by the electron because the electron's being pulled too far away. So now we have a molecule that has partial charges on it. That is called a polar covalent bond. I always think of the poles, right? You have North Pole and South Pole. So in this case, we kind of have a North and a South Pole. We have a positive pole and a negative pole. These are called polar covalent molecules. So here's that picture there. We have a slightly or a delta negative, delta positive. Now, an ion is an atom or a molecule with an electrical charge resulting from a gain or loss. So this is like, they're like, just take my electron or I am going to take, it's like, I'll give it to you or I'm going to just take it. So when an electron is lost, that atom is now positively charged because it has more protons than electrons. If an atom gains an electron, it's now negatively charged because now it has an extra electron. Now they both may now meet octet, but they have this stupid charge associated with them. So you know what they're going to do? They're going to hang out together. If they hang out together, the positive and negatives, they cancel each other out. And now the molecule, the overall charge of the molecule is neutral. We often tend to call these salts because salts, most of these ionic compounds make some kind of salt. So for example, we have sodium with 1 valence electron, right? Out in the outer orbital, or I should say electron shell, or energy level. Chlorine has 2, 4, 6, 7, all right? So again, we're gonna try to transfer that over. And so now I have 2, 4, 6, 8 in my inner level. So we've met octet, but now I'm gonna have a positive charge here. Here, now I'll have 8 around my chlorine, but I'll have a negative charge. So we're going to transfer that electron over, and now we're going to hang out together. And if I hang out, a positive one and a negative one is neutral. And here is a picture of that salt. So again, we're going to try to get our positives and negative ions. Again, an atom with a charge is referred to as an ion. We're going to try to get them organized so that we can put our negatives and positives next to each other. Now, the last type of bond I will talk about are hydrogen bonds, and these are very weak bonds. Right? So they're important when we talk about the shape of certain molecules, especially proteins. Now, hydrogen, again, remember, because hydrogen is kind of special here. When it's part of a polar covalent, remember, it has that partial positive charge. And so this charge region on the molecule, they're electrically attracted to that negative region on another molecule. And since, again, it's usually a hydrogen bonding with another element, we call them a hydrogen bond. So here's our water, right? So we have in here, remember, we have our polar covalent bonds, but now with that partial charge here and here, they're going to be attracted to each other. And we usually show this hydrogen bond, because it's between the hydrogen and the oxygen, as a dashed line. They're very weak. It's like static cling. So those are the hydrogen bonds that are going to hold the water molecules or make the water molecules be attracted, or remember, give us those cohesive forces. Okay, so there's our cohesion going on here. So remember that the structure of atoms and molecules determines the way they behave. So remember that atoms combine to form molecules. Hydrogen and oxygen can combine to form water. So notice I have 4 hydrogens on this side. I still have 4 over here. Over here I have 2. And I have, right, because I have 2 molecules, I have 2. So all we're doing is combining our, this is called the reactants to form our products. So the formation of water from hydrogen and oxygen is an example of a chemical reaction. So the reactants are converted to the products. Chemical reactions do not create or destroy matter. We're simply rearranging the atoms. So whatever we started with, we have to finish with. We started with 18 carbons. We're going to end with 18 carbons. They may be organized differently, but they're all accounted for. And that's conservation of matter. Right? So we talk about chemical reactions. The reactants is what we put into that beaker or test tube. The products is what we get out. So here we go. They're showing you, you can see in each of the atoms, 4 hydrogen, 2 oxygen, and then we form water. We still have our 2 oxygen and our 1, 2, 3, 4 hydrogen. All right, so I hope this helps you understand the periodic table a little bit better, how it's organized, why it's organized the way it is. And I hope you understand chemical reactions. And the 3 types of bonds, we did polar, we did covalent, we did polar covalent, non-polar covalent, ionic, and hydrogen bonding. So those are the things that you will be responsible for. All right, if you have any questions, please reach out to me.